Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome everybody. It's a bit rather different session than all the other sessions because I'm the only non-Microsoft session chair today. My name is Joost Pieter Katoen. I'm from Aachen University, so I'm not with Microsoft. Well, not yet. It's a great pleasure to chair this session. And the first talk will be given by Andy Gordon, and he's going to tell something about F7 security properties of F# programs by means of typing.
Okay, it's okay. I've got this.
You have this.
Okay, thanks, Joost Pieter. Well, it's great fun to be here. So this is I'm going to speak about F7, our system of refinement types for F#, and this is joint work with a bunch of people who've worked on it over the last 3 years or so. So some context. At last, in this decade, or last 10 years, we've made some real progress on software verification. I mean, like the 90s was like, you know, the decade of big progress in hardware, but I think this decade we've made a lot of progress. Sir Tony, who's not here, so I can be cheeky about him, calls it the Verified Software Initiative. I prefer the war on error. And this, my friends, is a war that we are winning. You know, we have got tools that can automatically and interactively find lots of bugs. This is, I think I'm heartened. We're at war together, but we're not all the same. There's a bunch of different tools, a bunch of different approaches. So think of C. I mean, you've got something like Coverity, which which is out of Stanford originally, about 10 years ago. And Coverity can automatically find bugs. It can't prove it can't actually prove the absence of anything, but it can find lots of bugs, and they're making a lot of money. SLAM came out of MSR Redmond, and it can automatically find bugs in device drivers, and actually can prove some guarantees about them. Say VCC coming out of EMIC in Aachen and MSR Redmond, is more interactive than the other tools I've spoken about. But it can actually prove really solid properties of programs. And CompCert, coming out of INRIA and elsewhere, is a sort of verifying compiler. Well, is a verified compiler for C that's also the basis. I mean, it has a sort of formal semantics of C inside Coq. That's the basis of, in principle, is the basis of like actually certified software tools that where you can actually certify in Coq that the results you get about your programs, say your C programs, are actually correct. So there's a bit of a diversity, say, in the case of C. Now, refinement types, which is the subject of my talk, is taking this battle to functional languages, and F7 in particular is a tool that can, where the philosophy is that we start from unmodified OCaml or F# programs, and by adding additional files that have got annotations with refinements on the types, we can actually verify properties of the F# code. And so for example, here's a very simple refinement type for the square root function, where in the unrefined type would be saying that square root sends a real to a real, and then the refined type is a kind of dependent type that you see here is saying that the precondition of calling square root is that the argument has to be greater than 0, and the postcondition is that the result is actually a root of the argument. So we've taken the base type real to real, and we've added some binders for parameters and results. And we also, in brackets, have these refinement formulas that are like subsetting the type to be the subset that satisfies the constraint. So reals such that x is greater than 0 is a subset of reals that are greater than 0. So refinement type checking blurs the distinction between type checking and verification. In that, we're used to thinking of, I mean, these verifiers here are have nothing much to do with the type system of C, but in the setting of functional languages, it's very handy to think about verification as a kind of enhanced type checker that starts off with a program that's well typed according to the standard type system for OCaml or F#, and then additionally we prove properties about of this sort, for example. And I think it's helpful to move away from thinking about type checking and verification as being different tasks. They really are the same thing. And ideally, we'd like the verification with refinement types to be done statically before you run the program, and also to be entirely automatic. And that's the ideal. In practice, often you have to have some interactive help, adding some hints to the type checker so that it can actually prove stuff. And sometimes in some refinement type systems, if you can't prove something statically, you drop code that will check some condition at runtime. So at least you get a runtime failure if an assertion doesn't go through. Now, there's a big variety of systems. I list a few there. Ours is F7. I'm going to go into detail about it, but it's quite related to a system FINE that's been developed in MSR Redmond, and the two are sort of merging together into something called F star, but that merge hasn't completely happened yet, so I'm mainly going to be talking about F7 this afternoon. Okay, so here, let me give you a sort of schema of the workflow when we're using F7. I'm going to give you some code examples subsequently. So the starting point is you've just got some ordinary F# code you want to compile. So that's what we see here. You've got your F# code, and you may also have an interface file that has like unrefined types like real arrow real in it. Then when we want to actually do the refinement type checking, we need generally to give to provide the refinement types as annotations. Actually, inferring the refinement types is like still an open problem. So you have to write some annotations on the interfaces. So that's what you're seeing here. That as well as compiling with F#, we have additional F7 files that have got annotations like the annotated type I showed in the previous slide. And we maybe have annotated interfaces for the libraries that we're using, such as crypto. And then the F7 type checker takes those and checks the same unmodified code that you're going to run. It may actually generate an interface file. But here's the type checking. How does it work? Well, partly it's done syntactically, but also we generate proof obligations in logic, such as, say that checking that a call to the square root function, the argument of such a call is greater than 0. That would be a proof obligation, and we would push that out to an external theorem prover. And we use an SMT solver called Z3 that comes from MSR Redmond, though in principle we could use a number of other automatic tools there. Sometimes we can't do everything with Z3, and we need to prove some auxiliary lemmas. And at that point, our style is that we write these lemmas in the F7 files, and sometimes we don't bother proving them. We just, they're sort of clearly true, but ideally, and we want to actually have a framework to prove them. So the way we do that is we can have a separate coq file that we can generate. That's, you see this file.v here that gets proved in coq, perhaps, or usually with the addition of some handwritten tactics. So it's a framework that lets you do automatic proof when possible and interactive proof when necessary. Okay, so what's the problem area? We didn't just develop the system sort of in a vacuum. For some years we've been working on looking at verifying cryptographic software, and we really saw refinement types as a way of doing better than the tools we had up until a few years ago when we started working on this. So here I've just got a couple of screenshots from the web of security advisories. The point is that getting cryptographic protocols correct is rather hard. There are design flaws in the actual protocols that are specified in international standards, and there's also implementation flaws in widely deployed implementations. And this doesn't seem to have stopped. There's been a lot of work on formal methods for these protocols, and yet these problems persist. People do, traditional crypto models such as the ones developed by cryptographers are also sort of more abstract models developed by formal methods people. Often miss out details, so you can do a verification in those abstract models, but it may not match the actual reality of what's happening on the ground in the actual code. So for some time, we've observed that this problem doesn't seem to be going away. Formal methods have been very successful, but still, people are still shipping code that has these kind of bugs in them. So we and others thought about 5 years ago that maybe if we could actually verify the implementation code, that would help. In part, because often the first formalization of these protocols is when people actually write reference implementations in C or in other languages. Beforehand, they don't have much incentive to completely formalize what the protocol is doing. So we figured if that's what people are doing, we should try and build tools that can take those early reference implementations and verify them. So there's been a line of work starting about 5 years ago. There was a tool called CISO that actually worked on C programs that was a heroic early effort that managed to sort of verify some very small programs but didn't give very strong guarantees. And subsequently, we also had a bit of work that wasn't looking at C. C is rather hard to verify, we discovered. I think everyone knows this. So we thought, well, hey, maybe an intermediate point between the formal models we know how to verify and actual runnable code would be something like F# or ML. So we built a tool called FS2PV, and PV stands for ProVerif, and it's an entirely automatic tool that's been developed here in Paris by Bruno Blanchet at ENS, and it takes an input in applied PyCalculus and can automatically verify things like various security properties, things like man-in-the-middle attacks, replay attacks, various impersonation errors and so forth, or secrecy vulnerabilities, this kind of thing. So it can automatically analyze that about, PyCalculus programs. And so we built a tool that would take ML implementations that you could actually run and do interoperability testing with C code, say, and we take that F# code and compile it to PyCalculus, and then verify it with ProVerif. And this worked reasonably well. In fact, we think we've generated more PyCalculus than anybody else by automatically running these tools. So it's great, but we found as we started to do really big case studies like TLS and Windows card space, that the runtimes are really long, like an hour or two, and they're also rather unpredictable. It's a whole program analysis, so it's really tricky to use. You'd make a small change to the input, and suddenly the runtime of the analysis would blow up. So our initial goal was to do better than ProVerif with refinement types. The promise of refinement types is that it's a kind of linear method that generates a bunch of proof obligations sort of linear in the size of the source code, and so it's going to be more scalable than, each individual proof obligation may not take linear time to prove, but at least you've got a linear bunch of them that you can try and prove individually. So that was our goal. So now what I want to do is give you an example of F# code that implements a simple protocol and show how we can use refinement types to do reasoning within the code. Okay, so the example I'm going to use is an authenticated remote procedure call. So the idea is that you've got a couple of machines that share a key, called key in this picture, and they want to send a request, or the client wants to send a request and get a response back. And in this case, I don't care about secrecy, and I'm assuming there's some kind of timestamp in these messages so that I'm going to know whether a message is fresh. But I want to make sure the message hasn't been changed in transit. So I apply a hash, a cryptographic hash, an HMAC, to the request with the key. So that means that an attacker on the network who sees these messages, who might be trying to mess with me, he can't change the request without, and still retaining a valid MAC. So any tampering of the request or the response will be detected. And I've also carefully put a tag into the request and the response, so there's no way to sort of take this MAC and make it look as if the MAC and the response and make it look as if it's a request. But there's still a glitch with this protocol. In fact, can anyone see a glitch? No, I'm speaking too fast. Or go on, Joe.
It's always about a nonce. Sorry.
It's always about a nonce. In this case, it's not a nonce. No, it's but good try. No, that's Needham Schroeder. This is not about nonsense. No, this is about correlation. There's nothing in this response message to indicate a correlation with the request. Okay, so the fix is that we should really include the request in this response, because you might have multiple requests at once and multiple responses, and the attacker could swap them without actually changing any of them. Okay, right. So let's have some code. No, let's have the informal spec first of all. So this is the kind of English language description. So this is the corrected protocol, where we've got, I'm showing a bit more detail, where we've got a particular encoding of the request S and the request and the response T, and then I've got some hashes on the request and the response, and I've taken care that the response includes the request. And these request and response functions are just kind of forming the thing that gets macked. So I'm suppressing the detail here of what the actual formatting is, but it includes tags so that this thing doesn't look like one of those. So you can't make a request because if it's a response. So the overall security goals is that I want that if B accepts a message from A, then A indeed had sent it. And secondly, that if, on the other hand, in message 2, if A accepts a response from B, then B has actually sent it and it was in response to a particular request. So that's the informal goals. And I'm assuming there's a population of many of these users, and ones that want to communicate already share a key, and that there's no compromise. So these are all like massive simplifications that we don't need in general, but for the sake of keeping this short, I've made this big simplification. So then finally some code. So this is F-sharp code that for the requester and the responder. So we've got client here and the server, and let's ignore the green stuff for the moment. And this code, say for the client, just starts up, makes a connection. He's got a particular request he wants to send, so he forms the MAC, and then he concatenates with that with the actual message, and then he sends it on the wire. And then over here, the server gets the message. He kind of unpacks it to get the request S, and then he calls the HMAC SHA-1 verify function that's going to check that the MAC is correctly formed, and he passes in that the MAC that he's expecting to see, request of S. And if they match, then we fall through. Otherwise, the thing will fail at this point. And similarly for the response. So that's the non-green code. The green code there is to specify the behavior of the protocol. So firstly, the assumes, think about those as logging events in some sort of global log. So I want to remember when, for example, here the client has started the protocol. So I remember that a client is running, he thinks he's A, he wants to talk to B, and the message he wants to send is S. And then when a response comes back, we log that this is B thinking he's talking to A. He's sending back a response T in response to a message S. So those are just adding events to the log. And then the assert statements are asserting things about the log that we believe hold. So we're using asserts. We're dropping the asserts in the code at the points where we believe, according to the cryptography, that something good has happened. So in particular here, after doing this HMAC SHA-1 verify, we assert that this thing is in the log. Okay, so this is the F-sharp code. You can run it. You can also pass it to FSTPV and analyze it with ProVerif. But we want to use refinement types to check this code. So I'm going to show you on the next slide how we add refinement types to the MAC functions so that we can prove that this assert is valid at that point. Okay, so, and this would be a good point also to make that, or just coming back a little bit, like there's a number of systems of refinement types. So some of them, a nice one, quite a famous one that's automatic is called DSolve. And it can verify refinement types where the formulas that are on types are quite simple. They're things like arithmetic properties or equalities, things like that. A distinctive feature of F7 is that we can prove much richer formulas expressed in first-order logic because we're using SMT solver to solve them, and also because we have annotations. So we've got to put in a few more annotations than you would have to have in something like DSolve. But on the other hand, DSolve can state weaker properties. So this is the kind of thing you can't do in DSolve, but you could do in F7. So that we have so HMAC SHA-1 is the thing that forms a MAC. And the red type is just saying that you give it a key in a bytes and it returns a bytes, which is the MAC. So that's the unrefined type. In blue, we've got the refinement information. And so the precondition is that you can only call HMAC SHA-1 if the parameter k is actually a MAC key. And also, it would better be the case that the formula MAC says km holds. And so MAC says km is going to be protocol dependent, and it's the property that, so to speak, the logical payload of hashing a message. I mean, it's in our example, the logical payload is given by this formula here, where we define that that MAC says k of m can be used in two ways, corresponding to the two messages in the protocol. Remember, the first message is a request, the second message is a response. So MAC says km for keys that are used in this protocol, keys that satisfy key AB, satisfy this formula. And so it's saying that you can MAC an m if it's a request, and this formula here holds, meaning that this thing is in the log. Or you can MAC m if it's formatted to be a response, and this response formula is in the log. Okay? So that's the precondition. So it means that in well-typed code, I just can't MAC something without having putting a suitable formula in the log. And then conversely, when I call HMAC SHA-1 verify after receiving a message, and this is before I do an assert that says that, say, a request has happened elsewhere in the system, when I call HMAC SHA-1 verify, I can use the post condition when I'm doing refinement type checking to show that that assert is going to be valid. So in particular, after doing an HMAC SHA-1 verify, I know that MAC says km holds, right? And then so that's actually generic. It's not specific to this protocol, but this specific formula here tells me that MAC-SAYS can only hold if the message is either a request or a response. And in the case here, just going back to the code here, I know the thing is a request because that's what I put in. And so it means that this formula here must be in the log. So that, in a nutshell, is how refinement type checking lets me type check this code locally. And you can see that the verification, proceeds. Well, you can't see it particularly, but you can maybe imagine that the way the type checker works is it generates a series of proof obligations. In particular, when you get an assert, there's a proof obligation that you must show this formula. And the type checker maintains a bunch of formulas that are true by virtue of postconditions and conditionals, and use those formulas to ask Z3 to see if it can prove the assert. So that's roughly, very quickly, how it works. All right, so that's macking. Now you might say that's a really trivial example. Well, look at this. Look at this. So this is Windows card space. So this is the thing that took ProVerif an hour to verify. So this is just the messages that are sent. This isn't even the F# code, which I think is about 1,000 lines. So we do rather larger examples than the one I've shown you. And here are our experimental results that we had at Popple last year. And the high order bit is that initially on very small programs, ProVerif is like super fast and there's no problem. But when you get above a threshold and you start getting into interesting programs like CardSpace or we're currently working on TLS, then the verification is rather faster using the refinement types. So you're seeing that here, that we get down to 6 minutes with F7 type checking for the 1,500 lines or so of CardSpace, where it's about over an hour with FS2PV. And the nice thing about this is that if there's an error, you know pretty much where it comes from in the source code, whereas with whole program analysis with ProVerif, it's rather hard to see where the error is. Okay, so that's the sort of technical part. There's a few frequently asked questions come up. So are there any? Oh, and there's one there. Great.
Do you take less than an hour to write out the types?
It probably did, yes. Let me, or actually, hang on, maybe I shouldn't say that. Because it's like 15. So hang on, I'm sorry, I'm getting excited here. No, it was less than an hour certainly for RPC. For Windows CardSpace, no, it wasn't. No, it would have been longer than that. But the point isn't so much the user time, but the fact that the verification is well, it's faster, but it's also more reliable, and you know where the errors are. It's incredibly frustrating trying to debug something when it takes over an hour to run. Okay, so if there's any cryptographers in the room? No, okay, so what cryptographers say is, Andy, that this is unsound. And they say that because they don't believe in formal methods and in symbolic views of cryptography, because the kind of models we use, something known as Dolovyau models, completely ignore the possibility that someone might guess a key. And cryptographers are uncomfortable with that, even though it actually is a way of finding lots of bugs. And they would like to actually prove guarantees, so they do it using probabilistic computational models. And so my colleague Cedric has worked on how to give F7 a probabilistic semantics, and so for small programs at least, he's able to use F7 to prove similar kind of guarantees that I've spoken about, but in the computational model. Okay, so are there any C programmers in the room? Okay, so the question we get from them is, but our security code's in C. We don't write it in ML, which is true. So we've got two answers. The first one is, well, we're writing reference implementations here. So Cedric, with some others in Redmond, did a great case study where they took this new protocol or cryptographic system called the distributed key manager that's used in Microsoft data centers. It's actually shipped. Okay, and so the code is in C#, and he did a reference implementation in F# that used exactly the same data formats, right? And it was rather shorter. They didn't want to ship it, but he used interop testing to show that. I mean, there was already a test suite for the C# code, so we showed that the F# code passed the same tests. So it was as close as they were, as the testers were, as far as the testers were concerned, it was identical to the C# code. It surely wasn't identical, but as far as testing is concerned, it was. And then he verified the model using F7. And so that was quite successful, and they were able to find some flaws and fix them. So that's one answer. The second answer is, Well, okay, so let's do the work, and let's move to C. So I think we always saw F7 as an intermediate point. We wanted to go to C. So in some recent work that's about to come out this summer, we showed how to take the theories of symbolic crypto that I've told you about, and we've moved it to VCC, and able to prove similar kind of results, at least for some small programs. So I'm rather excited about that, actually getting grips with verifying crypto properties of C. And we're also starting to work with BART on using Verifast to do something similar. Are there any functional programmers in the room? Okay, there's many. So functional programmers say, well, what about state? Functional programmers love the state monad. Well, so the state monad is a way of doing sort of stateful code within F#, where you have an implicit state or you make this sort of state explicit and pass it around. Well, we can add refinements to stateful F# programs, and you get things like this, where there's a precondition on the state and a postcondition on the final state. And this is similar to some work that Nanevsky and others have been doing inside Coq. And so we can modify F7 so we can reason about stateful code. And we've done some security work with that, and we've also done some work that's coming up at eCoop this year in a completely different area, where we take SQL table constraints and consider them as refinement types. And then we consider transactions on the database written in F# and show that they can't violate these table constraints. So we're quite excited about that. It's a way of preventing transaction failures at runtime. Okay, so let me conclude. We made lots of progress on verification. The F7 is flexible and scalable. We can beat ProVerif on some examples at least, and we've got this ongoing work on state, pointing to C and so forth. And Tony, we've got an advert here for your Verified Software Initiative. As I've been saying for a while, we should be calling it the War on Error. It's a catchier name. I mean, people have been talking about predicting the state of the art in 2030. I'd say even closer, say in 2015, that this application area needn't be the domain of special purpose tools, but instead we can use general purpose verifiers like VCC and Verifast, coupled with maybe some special purpose theories that have been validated in theorem provers to prove security properties of these crypto protocols and help to win the war. So thank you for your attention.
Thanks a lot, Andy. Are there any questions? Maybe in the meanwhile we can switch laptop. You mentioned in some of your slides that the idea, your aim is also to do compositional analysis. You didn't really stress it in your talk, but perhaps you can explain what's compositional about this approach in F7.
Well, it's compositional in the sense that the type checker just takes or composes together the results of many calls to Z3. We generate proof obligations, and we don't try and solve them all at once the way ProVerif operators. Instead, we have a series of calls. And if one of them fails, then you know which line it arose from. Whereas, if ProVerif fails, then you're kind of a little bit in the dark. Ben, and then Joe.
What are the obstacles to refine type inference, and are there other domains in which that seems to be more likely?
Well, it's surely undecidable. The people who are in the lead would be the DSolve folks, and Andre actually is doing some work on that with a PhD student. So or Andre actually, what would you say with it? Or what are the obstacles to refinement type inference? Since you guys have actually worked on that, whereas I haven't.
All the obstacles that you've heard of from tools like SLAM, BLAST, S3, essentially are the same. You can think of refinement type inference as invariant.
Yeah, it's like verification and type checking are the same thing. And what was the second part of your question?
Other domains, maybe more restricted domains, where it's actually somewhat like that.
Yeah, well, that's what DSolve does, where they limit the formulas to being simple arithmetic properties, where it's rather easier. Or where they limit the formulas so they exactly correspond to what the SMT solvers' decision procedures are. Whereas we've been a bit more reckless and throwing in quantifiers and stuff, where Z3 can often work, but sometimes just can't actually prove the problem. Joe?
Any experiences from external users?
Yes, we've had a few external users. I mean, there's people here in MSR INRIA, but also folks at Saarbrücken have been using F7, and they did some nice work on computational sounds, actually, which is an alternative to what Cedric has done. I should have mentioned them. Yeah.
My heart's going faster because
Oh.
That's Tuesday morning.
Okay, awesome. Well, we're making an installer right now, so I'll let you know.
Okay, I propose to thank the speaker again, and let's move on to the next speaker. The next speaker is Bart Jacobs. He's from the Katholieke Universiteit in Leuven, from Belgium, and he's going to tell something, I guess, about very fast.
Good afternoon. So I will be talking about our tool that we're developing called Very Fast, which in some sense has all of these adjectives applying to it. So these are true all in at least one sense. So it's powerful in the sense that you can prove many properties. I have to type actually. Hello, hello. Okay. Hello. Thank you. So it's powerful in the sense that you can prove many properties. It allows you to do inductive proofs over inductive data types and in recursively defined predicates and such things. So in that sense, it's powerful. It does require lots of annotation, so it's not very powerful in the sense of automatically proving many things. You can think of it as a very expressive proof checker. But the proofs are all in the source code. So the most of the talk will be a demo, so it will be clear what this means. It's sound, so what it says is true normally, but modulo any bugs that we've put in. So it's predictable in the sense that it's typically, or most often, it returns very quickly. So it's very unlikely that it will take a very long time before it gives you an answer. And I will explain why. So it uses a symbolic execution algorithm that is very simple and therefore very predictable in its execution time. And therefore it's also fast. And it's for C and Java. So it's in the scope or in the area of the following tools: VCC, Framacy, SpecSharp, Chalice, Daphne, ESC Java, most of which actually have a lot of are from Roostten originally, or derived from tools by Roostten Leno. So they're all verification condition generation based. So that's the main difference with Very Fast. Very Fast is not verification condition generation based. And one consequence of that is that the predictability of the execution time is typically not so good with VC-based tools, because these tools typically generate quantifiers, and SMT solvers are not always very predictable in how they deal with quantifiers. But of course, all the people that work on these tools work very hard to make it as good as possible, and there's a lot of progress in that. We try to avoid quantifiers as much as possible in Very Fast, sending those to the SMT solver. So that gives you the downside that it's harder to express certain things. It's easy to use a quantifier to express things. You can think of it as us approaching the same points. So they start from expressiveness and try to get performance. We start from performance and try to get better expressiveness. So another area of related tools is separation logic-based tools, other separation logic-based tools like Very Fast, such as JSTAR and Smallfoot. Those tools have the advantage that they automatically infer loop invariants and some loop invariants mainly. And the tools below, Space Invader and Abductor, even infer contracts. So Space Invader and Abductor are completely automatic, and they will try to prove memory safety of big programs. So Very Fast is very not automatic. That's the main difference. But it's more powerful, in that you can prove richer properties in Very Fast. SLAM is also a very important piece of related work where they use to verify device drivers. The kinds of target programs that we've been looking at include fine-grained concurrent data structures. So we have a paper at POPL 2011 on this. For example, we verified the functional correctness of a multiple compare and swap algorithm, which is implemented in terms of normal compare and swap machine instructions. We also looked at, or are looking at, device drivers, and in particular ones that you can unload, and this has consequences for the proof system, which we explain in a formal methods paper for this of this year. We also are looking at Java card programs, which run on smart cards, and as Andy mentioned, we're also looking together with Andy and Francois at crypto protocol implementations in C. So now the rest of the talk will be a quick demo of Very Fast. Okay. So counter, that's the first example. So this is a very simple C program which declares a struct counter with a field x. And let's first skip to the main method. So it allocates a counter, assigns 10 to the x field, reads it again and asserts it's still 10. This should, of course, go through, except it doesn't. But it's good that it doesn't, because the program actually has an error. Of course, malloc can fail, and in the case that malloc fails, it returns 0, and it doesn't give you any memory. And we can tell that it doesn't give you any memory because this part of the screen shows the symbolic heap, so the set of heap chunks, as we call them, that are in memory, and it's empty. So the heap chunk that we're trying to access, which is the field x of C, is not in there. So we have to fix the program. So if C is 0, we just abort. And now we can actually verify all the way until the end of the function. And we can actually step. Well, actually, let's first look at why it's not going all the way through. It says function leaks heap chunks at the top. And this is because, of course, there are some heap chunks left in the symbolic heap, namely the field x, and also the permission to call free on C. And at the end of the program, so we first have to free C before we terminate. And now this program goes through. So now we can symbolically step through the execution. And we can see how Very Fast operates. So it performs modular verification, each function separately, using the contracts of the other functions that are called by the function. So it always starts by assuming the precondition. And assuming means, for logical conditions, adding them to the assumptions, which is shown here in the middle. And for spatial things, adding them to the heap chunks. But this contract doesn't have any spatial parts. Now we come to the malloc statement, which in the case where we are, which is the case where C is not 0, it will add the x field, so permission to access the x field. This is a separation logic assertion, as well as the permission to call free on this pointer to the symbolic heap. So the symbolic heap contains both real pieces of memory and also more abstract notions of permissions, such as the malloc block chunk. Then we come to the if statement and then the assignment. And the assignment will change the value argument of this chunk to the value being assigned. So it becomes 10 now. And then when we read it again, we get value 10 in our local variable TMP. And when we get to an assert, we send a query to the SMT solver. But in this case, of course, it's trivial that 10 equals 10. So that goes through without a problem. And then free removes the chunks from memory. Okay, now let's make it a little bit more modular, this program. Let's use a function to create this counter. So we call create counter. Now we get to methods, the function create counter. And of course, we need to weaken the precondition in order to be able to run this function. If we run it again, Very Fast will complain that at the end of this function we are leaking memory because we are allocating some memory, but we didn't return it to our caller. It's still there after the post condition is processed. So we have to mention it in the post condition. And you can do that by simply writing the chunks in your post condition with their correct names. So we say we return the X permission as well as the permission to free the chunk. And now this will go through. Now this looks a little bit ugly, of course. This is not a very nice contract to write. So let's do some abstraction. we can define a predicate which takes the address of the counter and the value. So, I'm going to put this in a multi-line comment. And it says at the counter there is an x field. So this is another syntax for writing the counter underscore x chunk, whose value is value. And furthermore, we have the permission to call free on C. And now using this predicate, we can simplify this contract. Right, that's a lot shorter. Now if we run this, we actually get an error because very fast does not automatically, in general, does not automatically fold and unfold the predicates. So the constituents for the chunk are, for the counter, are in the memory, but the counter itself is not. So in general, we have to explicitly close this chunk. So this is a ghost statement that you can add. And now, well, this should be C. And now it goes through. Well, we get a problem here at the call side because here we have a counter and we need a counter underscore x. So we need to open it again. Luckily for these simple predicates, we can cause it to happen automatically by telling very fast which are the input arguments and which are the output arguments by using the semicolon here. And then very fast will automatically open and close the predicates. Now let's look at a method that changes, or a function that changes the counter. So inc takes a counter with some value. So this is how you can bind a value in a precondition, and which you can then use in the post condition. So we give back the same counter permission, but whose value is now the old value plus 1. So this is how you relate the pre-state and the post-state in very fast, by binding the old value using a question mark.
Where did you open, where did you close the predicate?
So it's automatically opened here. So if I, so you can also explicitly put the open, but actually you can see in the symbolic execution. So let me first fix the arithmetic overflow by turning off the arithmetic overflow checking. And now we can say run to cursor on the closing brace, which gives us a symbolic trace for this function. So if you go to the top, first we produce the precondition, so it ends up in the symbolic heap. Then we try to access this x field, but it doesn't exist. So we do the auto open, which will take the counter chunk off the heap and add the constituent chunks. And now we can access the x field and set it. And now we can close, we try to consume the new counter chunk. It's not there, so it will be auto closed. So we consume the two constituent chunks and we put a composite chunk on the heap. So we can now consume the post condition and we are done. All right. So much for the simple counter. Let's look at something more, more interesting data structure. Let's look at a stack. So we have a little C implementation of a stack with an implemented as a linked list. Each node has a next field and the value, and the stack itself has a head pointer. So in order to specify create stack, stack push, stack pop, and stack dispose, and in order to be able to verify this main function, so we push 10 and 20, and then we pop 2 elements, and we try to verify that the first element is 20 that we pop, and the second element is 10. In order to verify this, we need to be able to specify these functions, and in order to do that, we need to describe the shape of memory and the contents of memory using predicates. So first, we want to abstractly express the contents of the stack, so we want to use mathematical lists for this. And we can define in very fast a mathematical list data type. So type ins, for example, which is no ints or empty, for example, or ints of some int and some more ints. And using that, we can define a predicate nodes, which says that starting at some node n, there are some ints x's. So there are two cases. Either n is a null pointer, and then axis is empty, or n is not a null pointer, and then at n there should be a value field with some value, a next field with a next pointer. We also want to have permission to free this node, and we have some more nodes at the next pointer, which themselves have some value axis 0, and then axis is ints starting with value and followed by axis 0. So this defines both the shape and the abstract contents of a list of nodes using the separation logic predicate. And now we can do the same thing for the actual stack. So a stack at some position stores some ints if there is a head pointer at which there are some nodes which store axes. And also we want to be able to free the stack. Okay, now we can try to specify and verify the create stack function. So it requires nothing, and it ensures that we have a stack at result whose contents is empty. So let's see how this goes. We get through the function, but at the post state we don't have the stack chunk because we haven't closed it. But let's try to just auto close it. So we put a semicolon here and here. So that's very fast. We'll try to auto close the chunks. This means, so now we verified create stack, but we're stuck at stack push because its precondition is still false. So let's specify that one. We have a stack at stack with some values. And at the end, we should still have a stack at stack, but its value should be value followed by axis. And this goes through. So we specified stack push. Now we're at stack pop. So for stack pop, we have some values, and these values should not be nil. In the post state, we still have, we have some different values, of course. We want to say we have the tail, so I tail of axis, and we want to say that result is the I head of axis. So these are functions defined over this inductive data type, but we haven't defined them yet. So we can define I head of an ins using syntax very similar to ordinary C, except that you can also switch over an inductive data type. If it's empty, then we just return 0. If it's some ints, then we return x. And so this is a mathematical function. And the same for the tail. Okay, where are we? And the problem is here. Yeah, this should be empty. Okay, so we managed to get to this excess of head value. Here we have to explicitly open the nodes, because very fast only performs an auto open if it's certain that you will be able to find the chunk that you're looking for. And that's not the case. Well, I mean, using a conservative analysis, and since the nodes may be empty in general, this is not the case here, so you have to explicitly open this thing. And apart from that, the pop method also goes through. So now we're at the dispose. Notice, by the way, that the asserts were able to be proven. So if you look at the symbolic execution of the main method, so let's look at the state of memory. So after creating the stack, we have a stack chunk here whose contents are empty. Then after pushing we get a list 10 followed by empty. After the second push, we get 20, 10 empty. And then after the pop, of course, well, we get the tail of 20, 10 empty, so we don't do simplification yet of these things. In general, well, we have to do it, it's future work. So now we get tail of 20, 10. And so the program verifies, except for the dispose. But let me continue with something else in the last 5 minutes, namely a multi-threaded program. So let's look at a little HTTP server. So this is a little C program that implements an HTTP server. So let's look at the main function. So we create a string buffer which will hold, so the server will just accumulate all the requests that come in and show all of the requests at each response. In each response it will give you all the requests that have happened before. So it creates a string buffer to store the requests. Then it creates a mutex to protect this string buffer, which will be shared by the various threads. Then it starts listening on port 80. And then it sits in a loop accepting clients connections and starting a thread to handle them. And then in handle connection, we get the reader and writer ends of the socket. We create a string buffer to read the request. Then we acquire the mutex, append this request to the buffer of all requests. And then we copy all the requests into this buffer. We release the mutex, and we write the buffer to the output stream. So this program verifies. And why does it verify? Notice, by the way, if I move the mutex acquire, it will no longer verify because it cannot find the lock invariant chunk. If we remove this ghost statement, then it will not be able to access the requests buffer, which is what we expect. So how does one specify this program? So when you acquire a mutex, so let's look at the contract of mutex acquire. So let's run to this position. And let's look at here at the top, you see the contract of mutex acquire. It says, give me some fraction of the mutex chunk for this mutex, and it will have some lock invariant, P. If the mutex acquire succeeds, then you will get the fact that you are holding this mutex, which you need in order to release the mutex. And furthermore, you get P itself. So you get access to the data that is protected by the lock. And that is why we can then open this lock invariant. Notice that this uses higher order predicates. So this predicate here, this is a predicate name that is used as a value, as an argument to another predicate. And so this is where we define the lock invariant. It says I'm protecting the global variable that points to the string buffer for the requests, as well as the string buffer itself. And furthermore, so the second thing that we have to verify is the starting of the threads. So let's look at the contract of thread start here. So let's put assert false so that I can get a trace that reaches the thread start call. So if I go to this thread start call, I get at the top the contract of thread start. Oops. And it says, so thread start takes a run function and some data value. The run function has to be is thread run, which means that it has to comply with the type def at the top. So in very fast you can associate a contract with a type def, which defines a function type, and this allows you to verify programs that use function pointers. So the rest of the, so let's look at the type def. It says I take the thread run data for this data pointer. And the thread run data predicate is not a simple predicate, it's a predicate family. This is a notion defined by Matthew Parkinson and his colleagues. So I want the instance of thread run data for this particular function pointer and apply it to this data pointer. And the thread start requires that you pass in the data expected by the function pointer. And in the program, in the client program, the specific instance of thread run data is defined here. So we have a predicate family instance for the handle connection function, which gives you access to the socket. It gives you access to the reader and writer end of the socket, as well as to the pointer pointing to the mutex, and it gives you a fraction of the mutex itself. So notice we use fractional permissions here, so that multiple threads can each have read permission to access the pointer and the mutex. So here I end my demo, and I'm looking forward to any questions you have. Thanks.
Okay. Thank you very much. Yes, please.
You have inductive data types in some form of higher order predicates. How do you handle this if you translate this to an SMT backend?
So I don't translate these things to an SMT backend. The only thing that ends up in the SMT are equalities between chunk arguments. So these terms that you see here, they are SMT solver terms. And in order to match the specifications, the preconditions, the postconditions against this memory, I have to know whether two terms are equal or not. And furthermore, if you want to prove a logical condition given the assumptions, that also goes to the SMT solver. But the shape of memory is never sent to the SMT solver. Those things are completely handled by pattern matching inside of the tool itself.
Yes, please.
In the Spark system, we generate a lot of universally quantified stuff in verification conditions, almost all to do with the handling of arrays. Wherever you touch an array type, you get universally quantified stuff. So how do you deal with arrays if you don't like generating quantifiers? Right. So currently, array handling is a little bit painful in very fast. So we can do it, but it involves a lot of manual rewriting of the representation of the array. So let me give you an example of something that uses an array, for example, inverse.c. So I inductively define an array as being either nothing or an integer variable followed by some more integer variables. And then you have to manually rewrite this representation. If you want to access an integer somewhere in the middle of the array, you have to split this chunk into two chunks, saying the integers before and the integers afterwards. And you can do this using a lemma function. I didn't actually talk about lemma functions. In split, for example, here. So thanks for the question, so that I can talk about lemmas. So this is how you can do inductive proofs in very fast. This says if I have an array at array of length n, then I can give you two arrays, one that goes from array and has length offset, and one that starts at array plus offset and has length n minus offset. And you prove that by recursively calling inst split in the case that the offset is greater than 0. So you have to explicitly then split these arrays up and stuff. But we are working on automating this to as much as possible. But you're right. I mean, when you're dealing with arrays, quantifiers are very useful. But then it does become sometimes hard to control the performance of the verification.
Andre?
If you go for some sort of bigger projects, so what do you think is the ratio between the code and annotation?
Right. So typically what we see is for simple programs, currently we still need one annotation per line of code, typically. And for very complex things like the multiple compare and swap, we get until 10 or 20 annotations per line of code. But that's very complex, fine-grained concurrent code.
Final question.
Unspecified evaluation order of binary operators. So you've got, f of x plus g of y, and if g of y has a side effect.
Right. So very fast simply does not allow things that potentially have side effects as parts of operators inside of expressions.
And your analysis for side effect freedom is sound.
Yes, it's very crude. It just says only these types of operators. It's sound, yeah.
Okay.
Well, we think so, yeah. Because we simply don't allow function calls inside of expressions. You have to have each function call has to be on a separate statement. So that's a very simple approach. So I mean, so one to-do item is to accept existing C code. So currently, most of the code we verify is we have to first, almost rewrite the program to the subset that very fast currently supports.
Okay, I understand.
Okay, Thanks, Bart, again, for a very nice talk. And this brings us to the last talk in this session. This will be given by Marcos Darweit. He's from EMIC Microsoft in Aachen, and he's going to explain something about formula.
Ah, yes.
Okay. Yeah, thank you. Okay, so I would like to talk today about a modeling tool and actually about a modeling methodology that we at EMIC, together with our friends at MSR RISE, and you see quite a lot of persons have been involved in this effort, have been developing over the last 2 years. And the initial work is actually a little bit older than that also. And I would like to talk about one application area that we can use design space exploration for formula. And before we do that, I would like to start with the short motivation where we can use formula and the design space exploration tool in the area of embedded systems. So if you look at automotive, currently it's the case that there are more than 60 embedded control units working in a car, and this is basically software running all over the place for the head units, engine, brakes, wherever you can imagine. And the number of ECUs is actually increasing instead of decreasing. And the ECUs are also becoming more and more powerful due to multi-core architectures. So an observation that we made is that the manufacturers are currently in the process of trying to get more and more software onto a single ECU, and not to get rid of ECUs, but instead to put more software functionality on a single ECU. So the number of ECUs will not be decreasing probably. And also the complexity of the software systems is growing more and more complex, because we are not just talking about functional correctness, but also about specifying hard real-time constraints for these systems. We are thinking about energy consumption, safety, security. So there's a huge variety of different problem areas which should be addressed. So if you look at how embedded systems are currently developed, it's basically you start always with setting up a system architecture for the whole system, and then setting up the software and architecture components design, development and implementation for that. And once you've done that, you try to map the existing software components down to the platform. And in this process, you have to decide if you map different communicating components onto a network of nodes. It must be decided whether there's some communication required. So this communication must be configured and also set up. So you imagine that this process takes quite some time until you finally are at the executable, which can be tested or at least simulated. And the biggest problem is what happens if you encounter a problem during this process. So basically you have to go step up the whole process, or at least to the point where you made the mistake, reevaluate all decisions which were based on the wrong assumption, and you have to redo all the decisions again. So what we are proposing and what we are trying to approach this formula is to step in at the very first step in the system design and really support the developers already in that phase and allow to reason about certain properties about the systems that they are building. And the goal is to find solutions, or at least to assist the developers and find solutions that have a chance of being towards first time right. So an example application for formula, and this is really just an example application, because formula can be applied in a much broader sense. But this is a very common problem in automotive design. This software partitioning problem is something which happens all over embedded systems. So you usually start with a number of structured components, and then also specify a number of network of connected nodes with some communication links. And the question is, how can you really deploy the different software components and the communication links down to this platform? The interesting part is that these models are usually, at least when you're very early in the development process, they are not yet fixed. So they can still change the whole time. So basically, you are not working against a fixed set of properties. And the mapping is obviously very crucial, because the different components can, depending on where you map them, have completely different emergent properties. So the timing behavior can be different. If the nodes are different in some respect, the memory footprint can be different, and so on. So all of these needs to be considered. Also, the communication is very important because you have to basically plan that, ensure that the buses are not overloaded. And at the moment, so how this is done in industry is often that this is a task done by system expert who know from prior experience how such a mapping should actually look like. So they basically opt for adapting an existing system as less as possible, just based on previous experience. But the problem is still that this system can only be really analyzed and validated once you really have the system integration. So our goal is to provide some tool really allowing to do the analysis earlier than system integration. So this is a point where I would like to introduce Formula now. So Formula, as mentioned before, is more than a tool. It's really a modeling methodology. And I'm going to introduce this now based on the software partitioning problem. So basically, we talk about exploring architectures. So we have two very simple models. So we have an instance of functionality consisting of 3 different tasks with certain constraints. And we have a network of connected nodes with some channels. And the question is, how can we find valid mappings from these software components to the nodes and still guaranteeing that all the requirements that we might have specified are still fulfilled? For this, we use our tool Formula. So Formula is, at its very core, a formal specification language based on the logical programming paradigm. So it provides a common semantic for specific abstractions. So from the previous slide, you would, for example, for the functionality and for the platform, you would define independent abstractions within Formula and specify all the constraints that you need to specify in a single domain, as we call it. Formula, but also allows composition operators. So you can take these independent specifications and combine them together so that you can, in the next step, reason about the constraints that you have specified independently in a joint specification where you reason about all constraints simultaneously. And the final, in its final beauty, Formula actually also supports model synthesis and design space exploration, where the model synthesis is something where you only specify parts of your desired solution, like giving the task and the network, and leaving certain other questions just completely unspecified. What Formula then will do is it will figure out what would be needed to really instantiate this model to make it a valid instance of what has been specified in the composition. So you will be guaranteed that any result that Formula produces is a valid instance of your specification. The design space exploration then is able to enumerate over a lot of these different solutions and provide you with a lot of huge variety of different solution candidates on which you can reason. So how does this work? Now let's take a closer look at this example. So we have our 3 tasks, and the abstraction that we want to model is that there are things called tasks, which are marked here, that can be in conflict, which means that these tasks should not be deployed on the same node. So first, if you start modeling this, we have really to think about what are the entities of the abstraction that we want to talk about. So the entities are, if we look at the abstraction, it's obvious that the entities are tasks and conflicts. So what we do in Formula, we set up a domain, which is described as a unit of the abstraction. We introduce a type called task, which has as argument a string. So we can define the task, and we also introduce a type called conflict, which describes a relation between 2 tasks, specifying that certain tasks can be in conflict. Now we concretely instantiate this as a model and specify that this model, which we call instance, is of the domain functionality, and we can now concretely instantiate this using the existing types. So we define the 3 tasks, UI, voice recognition, and network controller, introduce some abbreviation for them, and can use the abbreviations in the definition of the conflicts, just as convenience. So continuing with the network structure, The abstraction that we are now modeling is that there are nodes connected by channels with certain capacities. So the nodes are these DSP, CPU, GPU nodes, and on each of these nodes that have certain properties, we can execute an instance of functionality. That means we can execute a task. Between those nodes, we have, as marked by these dashed lines, the potential for having channels. So we are not really specifying that there must be channels or that there will be channels, but in general, we allow that there could be connections, so there can be incoming and outgoing channels to the different nodes. And each of this channel can have a specific capacity. And there are two constraints that we want to specify. First of all, one constraint is that each node has at most 2 incoming and 2 outgoing channels, and that the capacities of these channels must be balanced, which means that the capacities of the incoming channels must precisely match the capacity of the outgoing channels, just to avoid the clogging of the different nodes with too many messages coming in and not enough messages going out. As you see, we call this a partial instance of an abstraction, because we specify certain things that must be there, like the different nodes, and we just leave the number of channels completely unspecified. In Formula, basically, this looks like this. So we have basically two language constructs in Formula that we can use to express the constraints we want to express. These are called rules and queries. First of all, let's take a look at a rule, for example, this one here. So for this type network, we've introduced again 2 types, node and channel, where channel has 3 fields. From and to, this is the direction of the connection of the nodes. And we have the capacity specifying the capacity of the channel. The rule must-bel is now something. This is operating on a set of facts, of a pool of facts, which are there for Formula. And the result on the left-hand side of the rules is produced if we find matches in the pool of facts which matches the right-hand side of the rule, which means we iterate over all the channels and look for a node which we apply to the variable n. If we found such a channel, which means a channel which is outgoing from the channel n, and we find another channel where the same node is the target of the channel, this means this is a candidate which must be balanced. Therefore, we introduce a derived fact must-bel for that node into the pool of facts. And now we can express some properties over the validity of concrete instances by specifying queries. So queries are Boolean operators also operating on the facts that we have in the state. So the precondition is that we are operating over all those nodes which we have identified before. So for every node which we have identified that it must be balanced, we sum up all the capacities of the incoming channels and see that and compare that with the sum of the capacities of the outgoing channels. And what we want to express is the avoidance of an error situation. So if we find a node where these two sums are not equal, this is a situation where actually a node can clog. And therefore, we express it this way. And you see down here, there's a second query. So this query conforms, which describes actually how a well-structured instance of this domain should look like. We demand that under no circumstances this query must ever be true, because if we have a clogging node, this cannot be a valid instance of the system. Similar things apply for the second constraint that we had with at max 2 incoming and 2 outgoing channels for a node. So we just count the number of instances and produce an error if we have more than 2 instances for the outgoing for the incoming channel, or if we have more than 2 errors, two channels for the outgoing channel. And again, we demand that these error situations should never occur, and therefore we negate this in the conforms query. So what we've done so far is basically describing the well-formedness of the functionality of the network, and the question is, how can we now reason about the possible mappings so that all the constraints that we've specified so far can actually be fulfilled. So what formula allows us to do is reason about these possible solutions that we have and iterate over all of them. So this is the design space exploration part. And formula allows us to iterate over those and produces us all the different solutions, or a lot of big variety of different solutions, from which I've now just picked 3 of them and visualized them. So what you see here basically on top is the software component structure. Down here are the hardware nodes. You see some arrows here representing the deployment. So the UI in this case is deployed to the DSP node, the network controller to the CPU, and the voice recognition to the GPU. And what you also see is that the network structure is now automatically filled in by formula, that there is a connection from DSP to the CPU with a capacity of 2, and there's also another outgoing channel from CPU to GPU with a capacity of 2, meaning that since this is just a circle and all these 3 channels all have the capacity of 2, this trivially satisfies the constraints we've specified for the platform. Also a little bit more complex example, but not yet much more complex. We have from the GPU 2 outgoing channels with the capacity 1 and 3, 1 incoming channel with 4. So this is also satisfied. Same here for CPU, and DSP has just 1 in outgoing channel with the value 1, with the capacity 1. So this is also satisfied. But as you might see, the right example is actually something which yields 2 unexpected situations, which formula also identifies. So first of all, there is this self-referencing channel where formula figures out that there might be a channel, at least from the constraints we have specified, which leads from the CPU to the CPU and has an arbitrary value. This is from the constraints we have specified so far satisfied, because we just specified that there is an outgoing channel and there is an incoming channel, and if there's just these 2 channels, the values must be identical. This is obviously, or this is also satisfied by this kind of channel, even though it doesn't make much sense. So what we would have to do here is actually enrich the specification of the formula platform model and avoid these situations. On the other hand, we see that this CPU and the other network of nodes is not really connected. Initially, you would think this is actually an error, but if you think closely about what we have specified right now, is we just specified that these 3 software components, these tasks, needs to be deployed somehow. We haven't ever specified anything about communication between the different tasks. So what would be the next step is that we actually annotate the models with more information, provide more information how these tasks are actually structured, how they are communicating. In that case, formula would be able to reason about that, and probably such a situation where you have different nodes which are not connected would no longer occur. So, but this is not just the end of the story. We actually would like to do much more. So we know from discussions we had with some partners that actually state of the art is that these hardware model and the software models are actually modeled in most cases in industry. Interesting gets it when you start thinking about extra functional properties like timing, resources, and so on. So the question is, how do you handle this if you add more and more of these types of constraints? So if you take energy, timing, memory consumption, different properties of the hardware nodes, so the reasoning in that case is becoming more and more complicated. So the challenge is, since basically these are all independent properties, you would like to find solutions where you know that all the types of constraints are simultaneously satisfied. And this is a big challenge. The question is, how does this work? So in our model, you actually always start with a component model. So this is the very core of everything. You have this component model includes the software model, the hardware model, basically all the structural constraints. What you then do is add independently descriptions about the system. So we call this facets. So a facet for us is a view on the system regarding a class of extra functional properties. This could be timing, memory, again, energy maybe. So what we notice is that most of these facets can actually be modeled independently, which means you can just take the this definition of that specific facet and relate that back directly to the component model without the need to model all these things simultaneously. So you just define your facet in such a way that it refers back to the original component model, enrich it with all the information that you need for this specific extra functional property, and that's all the description you need to do. The advantage is that at any point in time, once you have done the component model, you can just add these different facets in any order. So for us important, the description is independent, but the reasoning should obviously be not. So this outer circle represents the core solution space. It means all the constraints that could be satisfied by the type of structural constraints, for example, that are just there from the software component and hardware component model. Each of these facets now basically represent a reduction of the valid solutions just with a view of that single facet. So timing just restricts this, safety, memory, every facet is just a restriction. The interesting part is, where you would like to go, is to find this intersection here. Because this intersection is really the part where you know that all the constraints that you have been satisfied are guaranteed to be fulfilled. So classically, you would actually start just, if you would consider them not simultaneously, but sequentially, you would just select any solution from, for example, timing and try whether it fits with the other facet. If it's not the case, you would have to reiterate and look until you find the sweet spot here. And if you do simultaneous reasoning, you know that you will always be in the sweet spot because all the constraints that if model finding succeeds will be satisfied. Obviously, there's a drawback to this. So if you specify too many constraints, you might just overload the prover that is working in the back end. So you might opt for reducing the number of constraints that you put to formula and to the 3 which is working in the back end and reduce the complexity of the constraint so that you have actually a kind of over-approximation of possible solutions. This obviously requires that you would have to do some checking of the results later to ensure that any of the solutions that you get is really in the sweet spot here that you are looking for. But this has the advantage, on the other hand, because formula is very good at enumerating many solutions, that you just get a huge variety of possible solution candidates, and you just have to discharge them in a second step. So again, just a summary, what is formula? So formula is a formal specification language which is targeted at model-based development. Although I introduced it as here with an example from the automotive domain with the software partitioning example, we think that formula can be applied in many other domains, and we are actually doing this internally. Formula is based on algebraic data type and constraint logic programming, and as one of its key features, it supports model finding and design space exploration. Formula allows independent description but simultaneous reasoning about facet properties. And the nice thing is, as of last week, formula is actually publicly available for academic use. That means you can just download and try it out. It is integrated into Visual Studio 2010, so you can just, if you have that, just install it, try it out. Otherwise, if you don't have Visual Studio, you can also try out formula online at riseforfun.com/formula and see whether formula fits actually your needs. So if you have any questions, any more questions about formula, and see any of these 3 guys, so Ethan, Dirk, or me, just ask us and don't hesitate. Thank you.
Okay, thank you very much, Marcus. Any questions on formula?
Okay, yeah, thank you for this nice talk. My question is, how far can you go with this constraint? Because normally we not only like to specify structural constraints, but also behavioral constraints. I didn't see any behavioral constraints here.
Yeah, at the moment we are dealing mostly with structural constraints, but formula also supports transformations. So you can specify transformation, that means labor transition systems or something similar can also be specified with formula. It can also be evaluated, and we even support model finding through transformations. So some basic behavior can easily be modeled within formula.
Yes, please.
how easy is it to not only enumerate but also find possibly the best solution?
The best solution is a completely different problem because this would require some kind of optimization. So the techniques that we are using in the background is based on SMT, and on that technique it's a little bit more complicated to do real optimization. So what you can do, for example, is specify some kind of function and then do some weighing of the result and try to improve that and limit a bar every further down so that the SMT solver is forced to find a solution below a certain threshold. But this is not precisely optimization, and this is actually a research topic which we are looking currently into.
I would have
Yes.
a second question.
Yeah.
So normally if you do this mapping, you have two descriptions. One for the upper layer, one for the lower layer. And then only cannot be sure that they use the same description, but in your case, now you assume that the requirements and what is provided by the hardware layer, that this is writing the same language, in your language.
So yes and no. So we assume that the models that might be provided by the developers are designed in completely other way. It could just be models designed in any graphical modeling language or what have you. So we see basically two different roles. There's the role of the passive designer, or the designer which defines the types of constraints. And then there's the normal software designer, platform designer, which uses with the tools they know best. And we just take that information and convert that down to formula so that the real user doesn't see anything about formula. In that way, you can use this common semantic basis, which formula as a language provides, without having forcing the user to actually know about the whole background about formula.
I have a question about one of the constraints was energy. So I can imagine that you can use your framework for specifying energy constraints. But if you want to do that, you also want to have on the lower level, so to speak, you want to specify how energy is being consumed by the things. And that could be a kind of nonlinear differential equation or whatever way. Could that be done in your framework, or?
At the moment, at least if you think about differential equations or so, probably not. But we are thinking about how we can integrate such extensions into the formula language, or just integrate different tools. So one idea would be to model within formula just in a concrete domain as far as possible, and then apply this fitness function or the energy function with the concrete values in a later step, and do an invalidation of found models if this doesn't really satisfy all the constraints that you might have specified for energy. So it might be useful to have this multi-step process where you do the design space exploration in general and then apply more difficult functions which you cannot that easily express in formula in the second step, and do a weighing over the different models that you might get out.
If there are no further questions, then I would like to thank the speakers, Andy, Bart and Marcos, for the nice session. Thank you.